So previously, for a fixed compact Riemann surface X, we have associated to every holomorphic map from X to Pn some linear system. If the map phi is given by some tuples f0, fn, then we associate to it the following linear system. We let D be the greatest common divisor of div fi, and then we associate to phi the linear system corresponding to the span of the fi inside LD. So to every holomorphic map, we have established a linear system. However, not all linear systems arise this way. Only a specific type of linear systems called Basepoint-free linear systems. And so today we're going to explain what is Basepoint and why the linear system associated to a holomorphic map is Basepoint-free. This allows us to establish the following bijective correspondence, and thus we can think of holomorphic maps as linear systems interchangeably. So what's the base point of a linear system? Well, I'll just define base point of a collection of divisors in general. So if we have a collection of a divisor, we'll define a base point of it to be a point that lies in the support of all of the divisors. For example, here I have two divisors, E and D. Then a base point of this would be P, because P lies in the support of both E and D. Now, we claim that the linear system associated to a holomorphic map to the projective space must be basepoint-free. That means that it doesn't have any base point. There is no point P that lies in the support of all of the divisors in the linear system. Recall that if we have the map phi corresponding to a tuple Fi, then the associated linear system is defined the following way. Here D is the GCD of div Fi, so basically this linear system corresponds to the vector space spanned by the Fi inside LD. Observe that this linear system is just spanned by the following divisors. They are just linear combination of these divisors, the pullback of div xi, where xi are coordinate on Pn. They're homogeneous coordinate, but not really coordinate function, as they are not function. Thus, to show that this linear system is base point free, i.e. there's no point P that lies in the support of all of the divisors, it suffices to show that there's no P that lies in the support of all of the phi star of div xi. In other words, it suffices to show that if we take any point P in X, we can find one of these phi star div xi, so we can find an I, such that phi star of div xi does not contain P in its support. So let's look at a specific example to understand this, right? So let's say we pick Z is local coordinate, center at P, and so locally, in that local coordinate, let's say, suppose we write phi in terms of local coordinate, and let's say phi has this form. Recall that to evaluate phi at P, we need to choose a different representative of this map. So we will multiply everything with Z to the 5, and we get this representative, and then we can evaluate this at 0 to see the image of P. Now remember, by definition, this power 5 here is going to be dP, right? dP is minus of the minimum order of vanishing of the coefficient Fi at P. So dP is 5. And for each coordinate xi, the phi star of div xi, so the pullback of xi, that divisor, is going to have coefficient at P equals to this exponent. And this is not a coincidence, right? Because, why is that? Because how did we choose this representative for phi? We chose it so that we can evaluate this function at P, right? P corresponds to Z equals to 0. And in particular, we want these coefficients to not all vanish at P. First, of course, we want none of these to have a pole at P, so the order of vanishing of each of these coefficients has to be at P has to be greater than or equal to 0. But we don't want all of them to vanish at P, otherwise we'll get the point 0, 0, 0, which is not a point of the projective space. So at least one of them must have order of vanishing at P equals to 0. And that point will correspond to the pullback of some divisor of one of the xi. So that means phi star of the divisor of one of the xi is not going to have P in its support, and this is true for every P. So then we see that there is no P that can actually lie in the support of all of the divisors in this linear system, because they can't even lie in the common support of the pullback of the div xi. And thus, we showed that this linear system is basepoint free. Knowing that, it's now not very difficult to actually establish a bijective correspondence between these holomorphic maps with non-degenerate image up to coordinate change and basepoint free linear systems. right, on X. But why do we want to do this? Why do we want this new viewpoint? What's the advantage of this new viewpoint of linear system? Well, the advantage of this is that we can work now with the Riemann-Roch spaces. So remember that linear system correspond to vector subspaces of the Riemann-Roch spaces, and Riemann-Roch spaces have linear algebra structure. They have vector space structure, so we can use linear algebra to study them. Thus, we can use tools from linear algebra to study holomorphic maps from X to projective space. Thus, our natural next steps is to phrase statements about basepoint. We want to rephrase them in terms of Riemann-Roch spaces. We want to rephrase what it means for a point P to be a basepoint over linear systems in terms of the Riemann-Roch spaces, and then from that we'll deduce what it means to say this complete linear system is basepoint free in terms of the Riemann-Roch spaces. Well, by definition, P is a basepoint of this linear system if it lies in the support of all of the divisors in the linear system, right? So let us first rephrase the condition that P lies in the support of some divisor in terms of the Riemann-Roch. So let E be a divisor in a complete linear system associated to D. Now we want to rephrase the following phrase. We want to rephrase the phrase that P lies in the support of E in terms of Riemann-Roch spaces. So as E is linearly equivalent to D, we can write E as D plus the divisor of some meromorphic function. We call it Fe. And it turns out that the condition P lies in the support of E is going to be equivalent to saying that Fe lie in this Riemann-Roch space. The Riemann-Roch space is associated to D minus P. And let's see why that is. Let's observe first that as E is an effective divisor, by definition that means that D plus diff Fe is greater than or equal to 0. It's an effective divisor. That means that Fe must lie in the Riemann-Roch space of D, just by definition of the Riemann-Roch space of D. Alright, so now let's look locally at just the point P. Right? So in particular, we see that because E is effective, in particular this EP must be greater than or equal to 0. So the order of vanishing of Fe at P must be greater than or equal to minus dP. For example, let's take an example. Let's say that dP is equals to 3. Then what does this say about Fe? Then this says that Fe has a pole of order at most 3 at P, right? So that means that if we take a local coordinate Z at P, then and we expand Fe in terms of a Lorentz series in this coordinate at P, then it cannot have term of order power lower than minus 3, so it has to start from here. So this is what it means for EP to be greater than or equal to 0. Now what does it mean for P to lie in the support of E? That just means that EP has to be greater than or equal to 1, right? So that means that the order of vanishing at P of Fe has to be greater than or equal to 1 minus dP. In this specific case, that means this order of vanishing at P of Fe must be greater than or equal to minus 2. So that means that this first term here has to be 0. And this series actually starts from the term z to the minus 2. So for P to lie in the support of E, that's the same thing as saying that this order of vanishing at P of Fe here is going to be greater than or equal to minus dP plus 1. Right? In this case, it's minus 2 plus 1 is minus 2. So the maximum order of the pole has decreased by 1. Right? So the divisor of Fe now is bounded by the divisor D minus P instead. So this is equivalent to saying that Fe lies inside L of D minus P. This is what it means for P to lie inside the support of one divisor in a complete linear system. So what does it mean for P to lie inside the support of a linear system inside a complete linear system? So let's say we have a linear system Q corresponding to a vector subspace V, right, inside LD. Then we claimed before that for a specific element E and divisor E inside Q, to say that P lie in the support of E is just the same thing as saying that the corresponding function Fe lie inside L of D minus P, right? So then to say that P is a base point of Q is the same thing as saying that P lies in the support of all of these divisors in Q. That must be equivalent to saying that all of these function Fe corresponding to these E must lie inside L D minus P, but that's just the vector space V. So this is equivalent to saying that V must lie inside L of D minus P. Thus, we have the following recharacterization. P is a base point of the linear system Q corresponding to a vector subspace V, if and only if V lies inside L of D minus P. In particular, if we take Q to be the full complete linear system D, then P is the base point of this if and only if LD lie inside L of D minus P, right? But L of D minus P is a subspace of LD, so this is just equivalent to saying these twos are the same. And when X is compact, these are finite dimensional, so this is just equivalent to saying that they are gonna have the same dimension. Now, then rephrasing this, we see that D is this complete linear system, it's base point free, it doesn't have any base point, if and only if these two dimensions are not equal. But that will just mean that this dimension is going to be dimension of LD minus 1. So why is that? Why is this dimension either equal to dimension of LD or equal to dimension of LD minus 1? Well, that's because we can always view L of D minus P as a kernel of some linear map from LD to C. For example, let's say that dP is equal to 3, right? And let Z be a coordinate, local coordinate centered at P. Then every element inside LD has a Lorentz expansion at Z, but it cannot have a pole of order greater than or equal to 3 at D. So it must start, so the series must start from this term here. We can have the following map. We will send every element of LD to the coefficient of 1 over Z cubed. So what's the kernel of this? Well, the kernel of this will consist of element whose coefficient, this A minus 3 coefficient, must be 0. That means the elements whose Lorentz series centered at P starts with this term. That's exactly the element of L of D minus P. So L of D minus P is just going to be the kernel of this. And now, by rank nullity, we know that dimension of LD must be dimension of kernel plus the dimension of the image. And the image is either 0 or the whole of C, so the dimension of the image is less than or equal to 1. So we see that the dimension of L of D minus P is either going to be equal to dimension of LD or it's going to be equal to dimension of LD minus 1. This does allow us to rephrase the condition that this complete linear system is base point free in a way that is very convenient, only about dimension. Dimension of L of D minus P must be equal to dimension of LD minus 1.